Hi, everybody. Welcome. Thanks for joining today. This is the ground motion modeling topical workshop that was scheduled to be adjacent to the CRESCENT meeting in Seattle on October 30th. And we rescheduled it due to the federal shutdown to be 2 virtual sessions, and then we'll have an in-person workshop. So this is the first of the 2, and we're excited to have you here today. So thanks and welcome from the organizing committee. Our goals with this are first to kind of outline and showcase the existing state of the field as it relates to ground motion modeling in Cascadia, as well as the adjacent and kind of supporting seismology and science that's going on here. To think about defining priorities and thinking about building community, this cross-disciplinary community towards collaborative projects. And so this is the first of the 3 meetings. So the way that we've structured it is this meeting is going to talk about outputs. So what ground motion estimation in Cascadia needs to address from different perspectives. We'll have a couple breakout groups, and we'd love to get your thoughts and perspective in those groups. So we'll have more about those after the talks. On the 29th, we're going to have talks about inputs and data. So what exists that we can use in terms of science, data, as well as methodologies. And then in May, we'll have the in-person workshop in Eugene to talk about white paper review. And so for today, we have a handful of speakers. We've got Albert Kottke, who's going to speak first, Jeff Berman, Brett Maurer, Morgan Moschetti, and Karen Sung. And then we will have breakout discussion following that. So I think maybe we'll get started with Albert, if you'd like to share. And then also follow up if you could save your questions to the end, and we'll probably ask questions of everybody after the talks.
All right. Thank you, Valerie. Good morning, everyone, or whatever time is appropriate. Today, I want to talk about importance of spatially varying ground motion models and implications for Cascadia, and then some potential research questions that I think come out of that. So if we look at the last 20 years of ground motion modeling, back NGA West 1 in 2008 was sort of the first sort of modern implementation of ground motion models with a cohesive data set. And that pooled data from all tectonic regions into the models. In 2014, NGA West 2 was finished. And in that, they started adding regions to the models, and these group specific countries, and this was done on sort of a per model basis. So Campbell and Brazornia, they had attenuation for Japan and Italy, so then they separated China out, and they had one for, I think California was different as well. Abrahamson and all, they used a regional model for both the VS30 scaling and Alaska attenuation, and separated Taiwan, Japan, and China from the California models. And so here, these were sort of categories of differences. In 2016, Landwehr introduced the concept of spatially varying models. We have now continuous parameterization of the problem spatially. And then I would just point to NGA subduction, they had regional adjustments for basically the 7 different major subduction zones. But the idea here is that in 2008, we grouped everything together. And since then, we've learned we need to basically continually refine the model. And that has been driven primarily from data in the past. So what have we learned? So increased information has shown regions have consistent differences in earthquake ground motions. Initially, we interpreted earthquakes as being unpredictable, and that's mostly because the data was pooled all together and it clouded sort of our ability to assess regional differences. And this was essentially unmodeled error, so we're inflating our randomness to the problem. Now we're understanding that earthquakes are more predictable given enough data. And the spatial variation in ground motion is important, and ignoring it inflates the uncertainty of the ground motion model. And that uncertainty would be associated with the aleatory component, the randomness, when you just pool it all together and you ignore that. So when we think about development of ground motion models, especially in areas, large areas like Cascadia, we need to consider spatially varying parameters, but there's costs associated with this. First, we're going to increase the model complexity. So I think when NGA West 2 models came out, people were very frustrated with the complexity of the models. Well, if we want to do a better job of modeling the expected ground motion, the models need to be complex because they have to capture that spatial variation in source path and site parameters. And how these are modeled, we've typically been modeling these with Gaussian processes. And those processes, as you move away from areas with data, they start to inflate. And so this process increases the modeled error, and it penalizes the lack of knowledge or data with increased uncertainty, which is good because it says if you don't have data, then you can't assume that it's the average behavior. Just a little bit of the components of spatially varying models. This is from a paper from Irene and Norm, where they basically have an ergodic model. So here, this is the ergodic median as a function of magnitude, distance, and site. And they break it up into different spatially varying components. And if we just talk about class 1 parameters here, we have the differences in earthquake location. So we have delta location to location, and the subscript there is earthquake. So it just depends on the earthquake source. The path can be separated into changes in path as a function of anelastic attenuation, and that depends on both the earthquake location and the site location. We can do the same thing, but now think about changes. This should be, sorry, not anelastic attenuation here, but velocity. So changes in the velocity structure between those two locations. And finally, the site-to-site term, and that just depends on the site behavior. The interesting thing about these parameters are they're really biases that affect all ground motions. It's not an intensity-based driven or anything. It's not intensity driven or anything like that. And so weak magnitude, small magnitude events, large magnitude effects are impacted the same way. And in the past, we have been, I think, our interpretation of this has been clouded because we've worked on response spectra. And the response spectra do not handle very well the differences in magnitude scaling. And so as we move into the Fourier amplitude spectra to look at developing our ground motion models, we can do a better job of separating out these repeatable terms and in a magnitude independent way because of the way the Fourier spectra is. So I just want to talk about the site term briefly today because I think that's the parameter that might be the easiest to understand in terms of its importance. So if we look at this is a range of median site amplifications relative to 760 from the Alatik et al. Hard Rock model. And so this is one model we typically would use for our dam sites. And we can see that our ranging from a VS30 of 680 meters per second up to 2200 meters per second, which is sort of our range of rock conditions. This is the range of amplification that we see as a function of that VS30. On the right is if we have 760, what is our 5th to 95th confidence interval of that site amplification? And what we can see is that combining these, knowing VS30 tells you something, but it doesn't tell you very much relative to what your site could actually behave. And so uncertainty in the local site effects are much greater than the difference in median VS30. And this means that for rock sites, really it's much, much better to have recorded data than a measured velocity profile. And so we spend, this is the value of having recordings at a site, is it tells you where you are within this red cloud. Whereas if you had measured VS30, you would be somewhere within this blue cloud, but you could still be outside of that, right? Just an example of what that looks like. So for this was a site where we had velocity measurements, but we also had a few small magnitude, I think this was something like 8 small magnitude events from the magnitudes like 2 to 3-ish. We used 2 different approaches to evaluate the site-specific adjustment factor. And those site-specific adjustment factors are shown in blue here. We've got significant uncertainty on that just because of the limited number of recordings that we have. But you can see the site-specific factor in blue is outside of the 90% confidence interval predicted by that VS30 scaling. At PGA, it's a factor of like 2.5 relative to something like 1.2 amplification that we would expect from VS30. And so this is a huge difference in in loads for a specific site. And if we look at the velocity structure at this site, it makes sense why we're seeing this amplification. And if we just did simple site response, this is actually what we would expect to see. Um, the deeper, but it's much different than we would expect from just a typical VS30 scaling. And so when we think about applying ground motion models, this idea of VS30 provides us with a good estimate. It helps, but there's a lot of uncertainty associated with that. And as we move to informing ground motion models through observations at specific locations through these spatial varying models, we're going to start seeing differences like this. In some areas, we're going to see a lot higher ground motion, and in other areas, it's going to be much lower. And that's just a function of what data we have and the sort of assumption of, do we have average behavior everywhere, or is it really more detailed? So implications for Cascadia. We need to recognize that ground motion models are going to get more complicated, and they need to get more complicated to capture the spatial trends in the ground motion. This is going to move from unmodeled error, which is just randomness, where we throw our hands up and we say, well, we can't model it, so we're just going to assume it's random, into uncertainty, where we say, well, if we knew this, then we could model it, and it would be this. And if we don't know it, then it's going to have, it will be uncertain, and we're going to have to deal with those consequences. And this is going to allow for improved accuracy as more data becomes available or more information, and we can start improving that. The challenge is that for Cascadia, we might say that there's no data. I think that's the wrong way to look at it. I think that there's limited data, and we need to get creative in how we use that data to improve our models and calibrate them to the region. So some research questions that that come to mind in sort of how we move from our more ergodic models in Cascadia into more regional spatially varying models is twofold, sort of. One is, what is the behavior that's consistent between different earthquake sources? That is crustal, interface, interslab, and those oceanic fracture zones, the ones that are coming way off that are more frequent. What are the parts of the non-ergodic model that are consistent within these different seismic sources and which are different? For example, the site term, which is sort of just depends on the local site behavior, could be consistent between these different seismic sources, but it hasn't really been tested. Can we understand the physical reasons for where these might be similar or different and develop models that leverage that knowledge? I think this would be initially hard to do in Cascadia because of the limited data set, but we could start trying this in other places like Japan and Alaska, where we have more data to look at the similarity and differences between these different seismic sources and the non-ergodic effects. And, we've looked primarily at non-ergodic models from a lens of crustal earthquakes. So our distance metrics that we've evaluated the non-ergodic models to, for example, have been tested for crustal events, but do those same lessons apply when we start thinking about subduction events and interface events versus crustal events? Do we need to start thinking about different distance metrics or different non-ergodic covariance models? So this is more of a data-driven approach and looking at other regions to try and understand what we can learn with the data that we have. The other thing is simulations should be able to help us. And can we understand what about the region should be adjusted in our non-ergodic models? What are the physical reasons in geometry and geology, velocity structure, etc.? I think, and then could be used to adjust our non-ergodic models. Again, I think that it would be valuable we need to test, and we need to test against data that we have so we validate the effort, and maybe looking at sections of Japan where we have difference in behaviors between the south, central, and northern sections of the subduction trench. We have a wealth of data, and now we can test our simulations and say, can we predict what we see? And does the data support that? And then we can take that knowledge and apply it to places where we were not necessarily able to test in the same robust way. And that's what I have.
Great, thank you so much. I think we can take a few questions if there are any. You could either raise your hand or type them in the chat. We've got one from Dave Wald, who said, you mentioned that the class 1 terms are amplitude dependent, but if your amplitudes are determined by upgoing SH waves or horizontally traveling Rayleigh waves, which could be source or amplitude dependent, can't these terms be very different?
Yeah. Yeah. He meant independent.
Dependent,
And
yeah.
that's right, Dave. I think, what's interesting is we have thought about site term as only being site dependent. And maybe, I did a little bit of work on this, but coming up with, say, a distance dependence on the site term. So part of, like, if we were to partition out the site term into when you're close in versus far away, where your body waves or your surface waves are dominating the response, we might see differences. I think that would also be picked up in the path velocity structure term, where we're actually considering the difference between the earthquake and the site, and that behavior. But I think that that's like this formulation is one view of non-ergodic behavior, and it's not the final view, and that's not our final interpretation of the problem. And so understanding where these things are important or not, and for subduction sources, in some cases, I mean, especially for nuclear sites, it's hazard significant out at like 1,000 kilometers. And we use the same models that we would at close in. And so what does that mean? I think certainly that our site effect is different when you're far out or you're looking at subduction versus crustal sources, but we don't do a good job of considering that.
Thank you. And maybe one more from Ali. I think we can't quite hear you.
Hello?
Yes, that works.
Yeah, sorry. Yeah, it's just a comment or question. A few years ago, I was working on intensity of ground motions across the area, and I noticed that when I was looking at, for example, offshore cross-sol events versus the continental cross-sol on Vancouver Island, basically, the offshore events have a much larger attenuation compared to the continental ones. So is this something that like related to what you're talking here? Is this something that we can model with regard to these spatially varying models?
Yeah, I mean, I think you have to understand what the mechanism associated with that is, but I would assume it is probably some sort of, say it's a spatially varying anelastic attenuation parameter, or maybe it's something with the velocity structure that it's passing through that it causes different attenuation. But that's, in the past, for our models, we basically have one attenuation parameter that we're fitting over the entire region.
Yeah.
Right. And and that's not a right? We know that Q, for example, is going to be varying spatially. And we've always thought of that as being sort of, in a very broad sense, active tectonic versus stable tectonic have different Qs. Well, it's more complicated than that. In California, the coastal ranges north of San Francisco Bay have got very different Q than the coastal ranges south of San Francisco Bay. And they're really different. And if we just pool that data together, then it clouds our interpretation of what's going on. And so it's about understanding where there's differences and how to model those differences by looking at the data.
And just a follow-up, when we are talking about location by location, how do you define location? Is it just based on
Yeah.
how different the data is, or it just is?
So, location for location is hot. Site location is easy, right?
Yeah.
Every observation is at a seismic station, and that's one point. Earthquake location is much more difficult. When we think about non-ergodic models for crustal events, we look at the closest distance, and we look at that point as being the point that is defining the earthquake site, the earthquake location, and its relationship to that site. But when we think about larger sources, that might not be the case. We might have to start thinking about like where the primary asperity is, where the major slip. It might be defining the location might need to be refined because but mostly we're talking about, say, UTM coordinate.
Okay. Thanks.
Awesome. Thank you so much. That was great, Albert. Thanks so much. So that was a really great way to frame, I think, what we're hoping to talk about here. So the next speaker is Jeff Berman, who's going to talk about ground motion considerations for the built environment in Cascadia, if you'd like to take it away.
Sorry, lost the little box there. Yeah, let me share some slides. Thanks for the invitation to talk here. It's kind of interesting, a structural engineer perspective here, talking to a bunch, what seems to be a lot of seismologists. I know many of you. Let me just get the windows situated here. Okay, can you see the slides all right?
Yes, it looks great.
Okay, great. Okay, so I thought I'd give a kind of structural engineers kind of view on ground motion models and kind of what how we use them, just so people are aware of, I think, kind of the downstream impact of all of the work that's put into developing ground motion models. And I kind of cut this up into three little chunks here. So we have kind of structural engineering, kind of practitioner applications for new design of built environment, evaluation and retrofit of existing infrastructure components. And then those two, there's kind of two ways that we use ground motions and the motions themselves, and then ground motion models to help us select and scale the individual motions. And so there's equivalent static analysis, which really we're not using the ground motion itself. We're just using a single point off the spectra that's produced from a PSHA. And then dynamic analysis, where we're selecting and scaling ground motions. And for that, we may need a bit more information about what the underlying ground motion model or models actually are. And then there's kind of researcher, kind of my world, where we're trying to develop a better understanding of infrastructure component and system performance. And we may need ground motion models that can be used to inform scenarios. We may need ground motion models to help help benchmark some of the physics-based ground motion simulations that are being done, et cetera. So many needs for ground motion models kind of at the research level. And the result of a lot of the research that we're trying to do here is, and the way we're using the ground motion models, is to innovate building code requirements, understand the behavior of new special systems, develop fragilities that maybe have more context, that may be specific to region and types of structures, and then ultimately inform prioritization schemes for retrofit. And then, of course, agencies use the ground motion models for both for evaluating their existing inventory, for new design, and then there's state agencies that do a lot of regional loss estimation and planning and rely heavily on the ground motion models that are being assembled. So I thought I'd walk people through just those two things, the kind of design aspects first, what a structural engineering practitioner does with the ground motion models, just so everyone kind of is on the same page for breakout sessions. So we start with the USGS Seismic Hazard Model. For most buildings, they're designed kind of 85% roughly of buildings and bridges. They're designed really for a single point from that PSHA. The single point represents the spectral acceleration at the fundamental period of the building. There's a risk adjustment that's done, at least for how we use these in ASC 7, so that we get, instead of a uniform hazard, so a spectrum representing a uniform hazard and pulling off 1 point from that, we're actually trying to adjust it so we have a uniform collapse risk, and there's an underlying kind of assumed fragility curve that's used to make that adjustment. Oops, sorry, Teams is popping up here. It's slightly different what we do for bridges and buildings, but it's not too far off. Then once we have that uniform hazard or risk-adjusted uniform hazard spectra, we are really designing buildings, bridges for a single point off that. Spectral shape, for what we do for 85% of buildings, we don't care about spectral shape and we don't care about ground motion duration. The only thing spectral shape does to change is that 1 point on the spectrum kind of moves around depending on the shape of the response spectrum. But there's nothing that we're doing to account for period elongation of buildings or anything like that for the vast majority of new designs. Of course, ASC 7, IBC, they're all based on the California earthquake experience, and every little rule in all of the reference documents and how we do building design is based largely on our understanding of the behavior of infrastructure in previous earthquakes. And we haven't had, obviously, big earthquakes in the Pacific Northwest outside Nisqually that have really had any impact on building codes. And then both Oregon and Washington, of course, are in the process of adopting ASC 722. And there is this inherent kind of thing that we need to understand when we're developing, using the latest science and understanding to develop new ground motion models, is that when they go and then inform the maps, and it creates this kind of up and down kind of cyclic cyclic specification of the actual ground motion that's used for design. So 5 years ago, the ground motions were a lot lower. 5 years from now, they might be lower again. And then that creates kind of some pain for the design community. With every code cycle, the ground motions change pretty significantly. So that's just something to keep in mind as we're talking about updating all these things. And then for special structures, there's a totally different process that you can follow, a performance-based or code alternative design process. I have kind of one of the reference documents here that is the LA Tall Building Design Guide that's followed somewhat closely in many of the metro areas along the West Coast. And really, we're doing performance-based or code alternative design for tall buildings, long-span bridges, critical facilities, seismic design category E type things. We are, when we're doing this, we're developing site-specific response spectra and using site characteristics, available ground motion models. There's a couple different approaches recognized, at least in ASC 7. There's developing a site-specific risk-adjusted uniform hazard, similar to what USGS has done to produce the full maps. So you can go through that on a site-specific basis, or you can do a scenario-based development of spectra, otherwise known as the conditional mean spectra. Sometimes that's developed at a couple different structural periods and then enveloped. And that relies heavily on kind of the latest and greatest understanding and ground motion models to develop those spectra. Typically in the building design process or infrastructure design process, those spectra are used to do a preliminary, using some elastic structural analysis, a preliminary design. But then often we are doing nonlinear response history analysis with actual ground motions selected and scaled to that hazard. And so the ground motion models are very influential. We need to do deaggregation. Once we develop the conditional spectra, we deaggregate it. We understand which sources are contributing. we use that information and kind of even source specific GMMs to select scale ground motions that are specific for the sources. And that's more complicated here, I think, than it is in the Pacific Northwest, than it is in other parts of the West Coast. And then we're going to feed those ground motions through a nonlinear analysis of the structure. And there's rules in LA tall buildings to do that. And then one of the things I wanted to make sure we're thinking about in terms of new ground motion models is, we have now a pretty good understanding of what in ground motion actually impacts the response of structures, especially structures that behave in the nonlinear range, that are not kind of linear elastic oscillators, which is the vast majority of structures. And if I were going to put some emphasis or point to a few things to consider for ground motion models, they would be thinking about, especially for Cascadia, duration and spectral shape. We know spectral shape is extremely important. There's a number of studies going back to work at Stanford, Eads, Chandra Mohan. So that's Eduardo Miranda and Jack Baker's students and Craig Deerline's students. And we've done some work here at UW looking at kind of the impact of spectral shape on structural performance. And it's really significant, and it's very different in Cascadia relative to other areas of the country. There's basin effects. There's just the kind of character of Cascadia ground motions that produce different shape response spectra. And that really impacts buildings and bridges that behave in the nonlinear range. So the structure softens. It's not necessarily the elastic period that matters, but as your structure softens, you're maybe climbing the hill or you're kind of descending the hill, and that can have a big impact. And so as we're developing ground motion models, I think having some information about spectral shape and also ground motion duration is important. And I know that's been something that folks have focused on in the past. We can develop it on the infrastructure side. There's been a lot of work recently thinking about how does our assessment of performance of infrastructure change with ground motion type or kind of ground motion characteristics. And there's been a lot of work developing different intensity measures that kind of try to pick up on either duration, shape, some combination of those two things. And it really changes our understanding of the way things are performing. So this is just one little example where we had ground motions and we ran them through a bunch of different tall buildings, reinforced concrete shear wall tall building models. And we're looking at the probability of collapse of those ground motions versus spectral acceleration in this first plot on the x-axis. This is for two different ground motion sets. One that kind of represents MCER in Seattle, so it's got some subduction, but it's also got a lot of crustal kind of Seattle fault type earthquakes in there. And then the black dots are just using the M9 simulations that Aaron Worth produced and R. Frankel produced several years ago. And if instead we plot that collapse fragility on the x-axis, now not using spectral acceleration, but using an intensity measure that accounts for duration and shape, we get a much cleaner fragility curve. Those two curves line up, and we kind of pull out some of that uncertainty in ground motion as it propagates through our structural models. That can give us a much cleaner assessment, really reduce some of the uncertainty related to our assessment of structures. We use ground motion models quite a bit in the development of fragility curves, collapse fragility curves, through a process called multiple stripe analysis. And for those of you who don't know what multiple stripe analysis is, probably many of you do, we just take the hazard in terms of return period typically, and we develop conditional spectra for several different return periods, select and scale a bunch of ground motions, and we may even deaggregate the hazard at that particular return period. So kind of the contributions of different source mechanisms to the hazard may change with return period, and we can actually reflect that. And these conditional spectra, of course, rely on good ground motion models. And then so we may do that for several different hazard levels, several different return periods. So we'll have big suites of ground motions that we can then run through our structural models and then use the performance to, say, develop fragility curves for different performance states. In this case, it's illustrated with collapse. One example of some work that we did here at UW where we kind of used this approach, but also plugged in some physics-based solutions, the M9 solutions. And I think this is an interesting way of kind of combining our ground motion models and kind of what we've been doing in PSHA with physics-based computational solutions. So the M9 ground motions were really kind of the M9 simulations really represented just really that kind of band of large Cascadia magnitude 9 subduction zone earthquakes. So we kind of pulled that out of that multiple stripe analysis, and instead of selecting and scaling ground motions to GMMs, we put in the results of the physics-based ground motion simulations and combined that with the multiple stripe analysis with the ground motions selected and scaled representing all the other sources that might affect, in this case, downtown Seattle. And we kind of put those two together to be able to develop 50-year collapse risk that actually includes some of the new information that at that time was coming from those M9 ground motion simulations. And the results were, in this case, just illustrating 50-year collapse risk for 4 to 24-story reinforced concrete shear wall buildings in downtown Seattle. And we can see the impact of putting in those computational ground motion simulations in the square, substituting them in for that portion of the hazard versus just kind of directly scaling ground motions consistent with the 2018 National Seismic Hazard Maps or the 2014 National Seismic Hazard Maps. And it really has a pretty big impact, a factor of 2-3 difference on our understanding or estimates of the 50-year collapse risk for these buildings. And then from a structural engineering point of view, what we want to do is actually design, right? So we want to come up with solutions to reduce that collapse risk. And there's a couple different examples here of making structures stronger, stiffer, more ductile, et cetera. And then I just put out some kind of on the needs side. I think regional simulation, we're very interested in doing regional simulation as part of COPES Hub. We've been developing a very detailed inventory of bridge infrastructure in Western Washington so that we can develop much more kind of bridge-specific structural models, which then when combined with Cascadia-specific ground motions or ground motion models, of course, with site adjustment, which matters a lot, we can be producing fragility curves that are more specific, that are not based on, analyses of California bridges for California earthquakes. They're fragility curves that are based on what we might expect that reflect the kind of, things that make Cascadia ground motions different. So we're very interested in doing some of that. Again, kind of illustrating, I think from my perspective, kind of in the end user space, it's really duration, spectral shape that really have a big influence on what we see. So again, this is some data from Aaron's simulations back in the M9 project where we're plotting here. This is the Puget Sound kind of metro area. Here's like Washington, downtown Seattle's right here. And we're plotting this intensity measure that includes the effect of spectral shape and duration. And we can see that it doesn't look like a typical attenuation, like a typical ground motion model. It instead is really kind of reflecting the spectral shape and duration characteristics of the ground motions, and points us to locations that where shaking as it affects structures, in this case with half-second or 2-second period, might be really problematic. And then we can put all that information, we can kind of integrate that with our developed collapse fragility curves, and we can start to do kind of regional assessment of collapse, in this case, collapse probabilities for structures with different natural periods, and really start to do these kind of regional assessments. And so all of that relies, in this case, on computational ground motions, but you can do the same thing with updated ground motion models that have some of this, some of these important characteristics carried along. So again, not just worrying about the spectral acceleration at a particular period, but also, given that spectral acceleration, what are the likely accelerations at other periods? Okay, that's all I have. I think I took more than 10 minutes. I apologize.
That's all right. Thank you so much. That was great. We're a little short on time, but I think if there's one question, a quick question, we could maybe take it for Jeff. Great. If not, we can also ask them in the breakout rooms.
Great. Thank you.
Yeah, thank you. So the next talk is going to be by Brett Maurer. So now we're moving on to what are the ground motion needs for ground failure. So he's going to look at ground motions in ground failure, looking mostly forward and a little bit backward. And your slides look good.
Yeah, good morning, everyone. I'm going to talk about landslides and liquefaction, but my experience in Cascadia is much more on the latter, and so my talk is definitely biased in that direction. I think the motivations for looking at ground failure are obvious, at least in the forward direction. It's obviously a problem, both directly, but also through its hindrance on long-term mobility and recovery. It's also interesting to look at ground failure backwards. There are obviously a lot of paleoseismic indicators of earthquake recurrence rate, but ground failure can arguably record ground motions. And that's because we have models for predicting ground failure conditioned on ground motions, or at least ground motion intensity measures. And so we can invert these models and use them backwards. In Cascadia, quite a lot of paleoliquefaction, as it's called, has been found. About 5 years ago, we made an attempt to catalog all of it across 24 publications, and there were 185 study sites. Often these had dozens of features. And so one of the obvious questions looking at this evidence is, what can it tell us about 1700, if anything at all? I'll say a little bit about modeling ground failure really quickly and what the basic needs are from ground motions. Starting with liquefaction, I think models generally fall into 3 tiers. Tier 1 would be geospatial models. These are basically a guess of what's below ground. Some of these are really simple, like HAZIS, but they're getting more sophisticated, and the most popular models use PGA or PGV. Tier 2 would be simplified mechanistic models. These are the most popular models used by engineers in service of the building code. And by far and away, the most popular model uses PGA. Tier 3 would be our numerical constitutive models. These can give some additional insights spatially, temporally, used on special projects, and these use full time histories. Landslide models look very similar. We have geospatial models, our simplified mechanistic models, namely the pseudostatic approach, and then we have our constitutive models. And once again, for better or worse, PGA, PGV are often sought. And so this is potentially a challenge for simulations, given that the high frequencies are quite important to the engineering world, or at least to ground failure. I'll say a little bit about work we've done looking forward and looking backward before I talk about the broader needs. So looking forward, we did a study where we were able to come up with 400 sites with comb penetration tests. This would really be the gold standard test for predicting liquefaction. And we predicted liquefaction for 30 of the original M9 ground motion simulations. So these are 400 sites where we're able to use, among the highest quality models that can be used. And so on the right, we have the median probability across the simulations of manifestation. And so the probability of some expression at the surface. And what we see in the three major cities is that most of the study sites have probabilities of at least 40%. A lot of the coastal test sites where stronging is shakest didn't have, where the shaking is strongest, they didn't have susceptible soils. The soils were often too plastic. Obviously, there could be liquefiable soils elsewhere, and then there's really notable exceptions, like in Grays Harbor, Aberdeen, the liquefaction hazard is quite high. The scale of impact is really immense, liquefaction from California to Canada, as far east as the Cascades. And so I think fair to say liquefaction would be one important story in an M9 event. If I zoom in on just one place, Seattle, and say something about uncertainty here, these are the 2.5th percentile manifestation probabilities. I guess we might call this the best case outcome for Seattle. And we see relatively few study sites where the probability is above 50%. If I compare this to modeling work we've done on the Nisqually earthquake, I would hypothesize that the M9 outcome is actually less severe than in Nisqually. That's in the best case. If we look at the worst case, it's quite different. And I think the outcome would be far worse than what was seen in Nisqually. Now, the discrete predictions are great. If we want to get to saying something about transportation networks, we really need continuous predictions. I won't have time to say anything about the model here, but we essentially trained a geospatial machine learning model to surrogate or mimic the predictions of geotechnical models at the sites of in situ tests. And then in the forward direction, we can run the model anywhere where we obviously don't have in situ tests. So these are some of the median M9 results. This is the probability of ground failure. And in general, the predictions are the same as the discrete ones, but now we are spatially extrapolating in accordance to what a lot of geospatial proxy information is telling us. Those are the predictor features. So we've put a lot of these hazard maps online, both for subduction, but also for a lot of crustal events. Looking backward, we did a study a few years ago looking at 10 paleoliquefaction sites. These are sites that had CPTs or new CPTs were pushed. Alex Grant at USGS led this big effort to get the USGS cone truck to these sites. Deciding whether there was or wasn't 1700 liquefaction is pretty subjective, as you can imagine. We came up with a method where we tried to account for that uncertainty. And so we had sites like Cape Blanco in Oregon or Price Island on the Columbia River, where we gave it a score of 9. That meant we were 90% sure there was evidence of 1700 liquefaction. At the other end of the spectrum, we had a site like Lynch Cove on the Hood River. We gave that a score of 2, and that meant we were 80% sure there wasn't 1700 evidence at that site. As you can imagine, other people would come up with other numbers. So we asked the question, which of the 30 simulations better matches the field of evidence, at least as we interpret it? And broadly speaking, the simulations with stronger shaking in the south and weaker shaking in the north were more likely. That wasn't really surprising based on the distribution of the positive and negative observations that we had. But what was a lot more interesting, in my opinion, was that no simulation fit the evidence very well. So this is the simulation that fit the evidence best. And what you'll notice in the Puget Lowlands is we have pretty high probabilities of surface expression of liquefaction. And yet there's not a single paleoliquefaction site where we have proposed or favored or apparent cause from 1700. And so there's this question of where is the evidence? It could just be that we haven't found it. It's hard to find, really hard to find. It could be that our models, our predictions are just wrong. Can't rule it out. It could be that the 1700 motions truly were less than the M9 simulations, especially in the northern parts of Cascadia. And if that's true, why? Was it not a full margin rupture? There's a lot of possibilities, and it's an open, intriguing question. So to say just a few things about key needs, and this is heavily biased towards liquefaction, towards regional scale analyses, and towards physics-based simulations. So this is not really aimed at the empirical GMPEs. So first, obviously the soil is really important for these intensity measures of engineering interest. It's obviously not surprising if they change by 100% or more. For understandable reasons, the physics-based simulations often don't include site response, meaning the prediction of site effects. Ideally, they would somehow. And then to take that further, ideally the uncertainty of the site response would be characterized in the physics-based simulations. The uncertainty of the velocity model is really big, even at sites of measurement. So we do a lot of MASW modeling in the region. And so this is a shear wave profile derived from ASW modeling in Seattle. And even with measurements, the uncertainty is large through these surface wave inversion methods. If you don't have field measurements, it's obviously really large. Going further, there's also a lot of uncertainty in the soil traits, which we need to model nonlinearity. And so what we essentially have to do at regional scale is we have to say, for all locations and all depths, we have the same soil, some sand with some properties. And that's obviously not true. Even if there's no uncertainty in the soil profile whatsoever, how you choose to model nonlinearity can also be really important. So these are some site response analyses, PGAs, predicted by two different techniques for capturing nonlinearity. We have a time domain true nonlinear site response analysis on the y-axis, and then we have a frequency domain equivalent linear approach on the x-axis. And when the strains get big, meaning when the soil is soft and the shaking is strong, it can make 100% difference depending on which technique you choose. And there's not necessarily a good consensus on which is best. I mean, some are better conceptually, but then in terms of which is actually more accurate, it's not so obvious. So there's a series of uncertainties that all are compounding, and they seem to make a really big difference. Specific to the backward analyses, there's a lot of paleoliquefaction evidence without dating. So all of these markers have paleo evidence. And then these are the sites with maximum radiocarbon ages. And these are the sites with minimum ages. And the point is, most of the sites don't have dating. And so there's a real opportunity, particularly in the Puget Lowlands, if more of these sites can be dated, it could really change or confirm what we currently think about the 1700 ground motions. And then finally, we really need subsurface data. On the right, I'm just emphasizing these are our machine learning predictions, and we only have a high degree of confidence at the purple dots where we have cone penetration tests. Everywhere else, it's essentially a very sophisticated guess. And so the more subsurface data we can get, the better. I think the floodgates are about to open due to AI. I mean, we're almost at the point where vast amounts of geotechnical documents are going to be able to be read and extracted. And I think at that point, anyone who has ever spent a lot of time trying to digitize paper documents will probably feel very sad. But it's all going to be for the best. So with that, I am done. Thank you.
Wonderful, thank you. I think we have time for one quick question, and it looks like Kim Olson has one in the chat. He asks, which physics-based scenario simulations may help structural analysis in the future? Are the M9 simulations sufficient for megathrust events? If not, which scenario simulations may help crustal events? In other words, which scenarios and bandwidths should the physics-based models focus on?
Well, it sounded like that question could even be directed to Jeff as well. I guess I would just reiterate the point that for ground failure, specifically, particularly for liquefaction, the high frequencies they continue to be the most efficient and sufficient intensity measure for predicting ground failure. And so, as I understand it, it's really the most difficult, challenging part to get right in the physics-based simulations, the high frequencies. But it's nonetheless the case that, at least in my mind, that's the most important part.
Yeah.
Thanks, Brett. How high frequencies do you want to the physics-based models to include ideally?
Yeah, well, since you put the word ideally in there, let's go with infinite or, I don't know, 10 or 20 hertz. But, realistically, the answer is as high as possible. I don't actually have a great sense on precisely where does PGA stabilize, but I guess that would be the answer.
Okay.
Thank you.
It's easier for structures. I think if we can get down to half a second, two hertz, which on these big Cascadia models is still quite challenging, right? But maybe possible for crustal. I think it is possible for crustal fault models. I think that the really high frequency isn't, that's not really a concern for structures. I think if we can get half a second, that's really good.
Thank you. All right, so we're going to move to the next talk, which is the NSHM perspective. Morgan Moschetti will be talking about ground motion modeling in Cascadia for the U.S. National Seismic Hazard Model, current modeling approaches, and open questions.
So, thanks. My name is Morgan Moschetti. I'm from the USGS. I'm presenting here on approaches to ground motion modeling in Cascadia for our National Seismic Hazard Model. And so what I'm hoping to do, this will be a pretty basic presentation about the approach that we take for ground motions in the Cascadia region, mostly focusing on subduction zones, but with some comments about how we model crustal earthquakes too. And then I'll just leave some kind of open-ended questions at the end. So ground motions in PSHA, that National Seismic Hazard Model, is a probabilistic model forecast for ground shaking. Essentially, this is suites of predicted ground motions for different scenarios, or all of the important scenarios that are developed in the seismic source characterization or earthquake rupture forecast. So in the Western US and Cascadia, so this is both for the subduction zone earthquakes and for crustal earthquakes, we're using empirical ground motion models or semi-empirical ground motion models. These provide the median ground motions and an estimate of the standard deviation. And most of the presentation here is going to focus on effects of the median, but standard deviation is also a really important part, as we just heard earlier, in terms of its impact on hazard curves. So, a role of the USGS in this process is selecting and combining ground motion models, also modifying them as we see needed. And there are a number of places where the broader community gets involved in this effort. So I'll just take a couple minutes to talk about these semi-empirical ground motion models that are used for seismic hazard. I think most users here are familiar with the kind of linear decomposition of ground motions into source, path, and site effects. And the empirical ground motion modeling community uses a similar parameterization. So the expression that's shown here is for the mean natural log ground motion, which has this constant term, and then a path term, magnitude dependent term, depth effects, and then site effects. And so although these are done for response spectral accelerations, they've used this same parameterization. And so an important thing here is that any better understanding about all of these components can be brought back into future ground motion modeling updates, and they've regularly refined the functional forms that are used for these expressions. And so this is an important part for contributions. Also, there are these direct contributions that may fall slightly outside of the ground motion modeling and may relate more to shallow uh, site characterization or regional seismic velocity characterization, but these things can be directly used in the hazard calculation. And so specifically, I'm referring to VS30, Z1 and Z2.5, which are parameters for the basins that we have in this area. So on the right are just some examples um, of the empirical or the ground motion models that we have for various regions. And so, important things here are that there are offsets in the amplitudes at the near source region. There are differences in attenuation. And then also not shown here are important differences in the site effects and basin effects. So as we heard in the first talk, a really important contribution to Cascadia ground motion modeling that was incorporated recently are the results from the NGA subduction project. So this is the most comprehensive ground motion data set for ground motions from subduction zone earthquakes. They compile data globally, and as we heard, they developed both global models and these regionally adjusted models. In Cascadia, there are regional effects that are now incorporated into the ground motion modeling that were not previously included. These include regionalized site response, so the dependence on VS30, regionalized basin effects, inelastic attenuation in some cases. This is just a depiction at one magnitude and one intensity metric type of the range of ground motions that you get from the different regions. And so there's a pretty significant regional effect, both at the amplitudes at close distances, and then also some of these effects that we understand a little bit better in terms of attenuation with distance. And better understanding really on the global contributions of structure and subduction zone geometry and all of these other factors could be important to improving ground motion modeling in Cascadia also. Finally, I just want to mention that because this is that probabilistic calculation, we can use a logic tree structure to incorporate alternative models. And so these are important ways to bring in alternative modeling approaches that are used in hazard. This is already done in Cascadia, so we use various ground motion models. We use estimates of uncertainty that are provided by the ground motion, a number of the ground motion modelers. And recently, we've also used logic trees on some of the basin effects that I'll describe later. So just to kind of step back and see some of the basic limitations in Cascadia. So these are plots of the magnitude and distance depiction of the ground motion data sets from NGA subduction. On the left, these are the ground motions for interface events, and on the right are the ground motions for slab. The colors correspond to the various regions, and green is for Cascadia. So as we all know, there's essentially little to no data from interface events in Cascadia. So this is obviously a huge uncertainty in terms of developing the ground motion models. And the ground motion modeling groups in NGA subduction took different approaches, and so that's an important uncertainty that we're already including. Some used something like a global average. Some looked at analog subduction zones, but better understanding on where Cascadia falls within kind of the range of global subduction zones and implications for ground motions is an important contribution that could be really directly incorporated through the selection of GMMs. For slab earthquakes, as we all know, there's a much better availability of data, including the recent Nisqually events. These events are more frequent, including in the historical record and instrumental record. And so this is an important part to hazard in the region, especially at shorter periods where they can control ground motions. In terms of the slab ground motions, there's still some fundamental questions that we have because we don't have a lot of recordings from large magnitude events. And I want to highlight one that's really important here. On the plots in the top row here are ground motions from the Nisqually event at two different periods, and so at 0.2 seconds and 2 seconds. We can see the effects here of the basins and the Cascadia really standing out, and that's a feature that's being incorporated. This bottom panel, however, is an important piece that has been addressed in a certain way, and I want to describe it here. So this is essentially showing the bias or the average log ratio of observations to predictions for various GMMs that are currently used in NSHM. Because of limited data from slab earthquakes and also questions about the distribution of available data, there was a choice by most of the ground motion modeling communities to not directly use the amplitudes that were observed in Cascadia to inform the GMMs for this region. And so the result is that the ground motion models predict higher amplitudes than are observed historically, and that's also the case for Nisqually. So we have one model where this is one of the versions that was provided by the modeling team that largely matches the observations. But at short periods, we have an overprediction of these observations. And this is true both for Nisqually and also for when we go back and look at all of the ground motions for the region. And so this is not like a surprise that the modelers are aware of this. This was a choice in modeling, and further investigations to understand this better and decide if this was an appropriate choice or if there could be other choices that could be included is important. In the region, there's also a unique site response that they identified, and this was first incorporated with NGA subduction. So site response is the variation in amplitude with VS30 is the primary way that it's incorporated. And as you can see in these log plots, they use this linear fit, which is appropriate at the range of periods. These plots are giving the coefficient for the slope of these curves. And as you can see, Cascadia is this pink curve, and it falls kind of in the middle here. It's slightly different than what's used for active crustal. Right now, we're attributing this at all sites that are affected by subduction zone earthquakes. It may be more appropriate to limit where we use this site response to sites in certain areas of the Northwest, perhaps even just some subset of those areas. Ultimately, we may want to apply these models also to the crustal ground motion models. And so there's some really basic questions about what controls regional site amplification. Can we better understand the spatial extent of these effects, which are presumably related to geology? As was brought up earlier, I think there are basic questions about if the site response varies with source depth, the type of event, distance, azimuth, other factors. And there have been studies that have highlighted a number of these features, but have not yet been included. I see I'm already over time, so I'll go very fast here. I do want to say that we included basins in the Western U.S. broadly, but also in Seattle and Puget Lowlands area. These are included in this kind of patchwork approach. Initially, we've really focused on the effects of deep basins and long periods where there was concern that the ground motions were very different. Increasingly, we've had feedback from the engineering community that also characterizing shallower basins is important. So there's motivation to further refine these models, and as we heard earlier, perhaps have alternative models. So we know there are various basins in the region. The ones that have been best studied are certainly in lowlands, and so there's really opportunities for very basic contributions. I will say we introduced a relatively simple basin model for the Portland and Tualatin basins with a ground motion analysis that's described here, and so that's an area where there's some basic work, but also could be further developed. We've heard quite a bit about simulations, and that's certainly an area that will move forward. Right now, we're including basin amplification and one logic tree branch for basin amplification from 3D simulations. These are examples of the range of basin amplifications from the various empirical GMMs, and then one that was guided by the M9 simulations. And so really we're seeing these factors that were developed in the Wirth et al. Paper from 2018. Future studies with simulations can further refine these. Perhaps we could use something like this for crustal earthquakes in the area, but there are a lot of opportunities here. And so the last thing I just want to leave here, and these are really big picture questions that haven't been addressed and I think are really important. I touched on this one about slab ground motions and whether the future earthquakes will have lower than global ground motions or be more similar to global averages. Interface ground motion amplitudes, we know that there are very unique characteristics of this Cascadia subduction zone in terms of temperatures, age of the incoming plate, and those may have important consequences for interface ground motions. And so one that's been highlighted here that we've seen in some of the very large magnitude earthquakes are these strong motion generating areas or high stress drop. I think it's an open question if that is going to hold for Cascadia. Simulations I've already touched on, and so there's quite a bit of work here that could be done. Finally, I'll just say that there's work for crustal fault sources to incorporate the effects of rupture directivity. This has not really been started, or is it less mature, certainly for subduction zones, but this is an important feature that came out of the M9 simulations and could be used to further refine hazard in the area. So I'll stop there. Thank you.
Great. Thank you very much, Morgan. Yeah, so Karen is going to talk about the empirical ground motion modeling perspective. She'll talk about implementing simulations in ground motion models, practicing practical needs and challenges.
Okay, so in this presentation, I will discuss the practical need and the challenge of applying simulation into ground motion model. As we know, big earthquakes don't happen that often, so we don't have enough empirical data to constrain the result at short distance or like the deep basin. So let's look at the plot on the left. These are the 30 simulation runs for the M9 event from Frankel's there 2008. Yeah, it's 30. So the blue area is the study site in Seattle. Now move to the middle plot. This is the result for a 3-second simulation for the study site. You can clearly see how the large amplification in the Seattle and the Tacoma Basin. But if we look at the right plot, which is based on the standard we call the Agouti model here, those basin features are gone. So that's because the Agouti model just average everything out and don't have enough data to work with. So our goal is to take this feature and add them into the non-Agouti model. This way we can bring this physical behavior into our model. And here just show the process that applying the simulation into the ground motion model. To be clear, we are not building the new model using simulation directly. We start with a Agouti model and use the simulation to spot the difference, and we call it a non-Agouti term here. But there is a crucial first step. We need to constrain the basin scaling using simulation. That is the basin scaling in the Agouti model here is AG22. It's modified to consistent with the average scaling from the 3D simulation. So once we have repressed the basin scaling here and we split the remaining difference in two parts, first one is the non-Agouti term, the delta NE term in the left-hand side you can see here. This is a spatial map you can see on the bottom plot. It captures the amplification in the Seattle and Tacoma Basin right now, like previous slide you observed from the simulation. And we use this to modify the Gaudy model. The second term is the CSIM, a constant shift that accounts for the average bias between the simulation and the GM. So by moving to this non-Gaudy approach, we can reduce the oscillatory variability. You can see here from the dashed line to the triangle part, you can reduce the oscillatory variability. Also, it allows to capture the epistemic uncertainty of non-Gaudy term based on the simulation directly. So we can use all this into the seismic hazard analysis in the further. Yeah. So now the first big challenge when we use the simulation into the ground motion model is path coverage. Since these simulations are based on the single M9 scenario, each side only has the source from limit angle. So this makes it hard to separate sine effect from the path effect. So the non-algorithm here, the delta NE, is mix of both sine and the path effect together. If you look at the right plot, what looks like the pure sine effect actually is into the path part. So how do we fix this? First, I think we need the scenario with better atmospheric diversity. Second, we must validate this with small earthquake in the M3 to M5. Those are the cases where we have enough empirical data to verify if these simulated spatial patterns are stable or realistic. Yeah. And second one is resolution. You can see the left plot, the group 1 here in Seattle has a dense 1 kilometer grid from simulation, which is fine enough to capture low space and effect if we look at middle plot, the same region. But for the border Cascadia on the left-hand side, the black dashed line here, the group 2, the green jump to the 20 kilometer. It's simply too big. So the middle plot, the scaling of the non-algorithm in outside Seattle is weak. It doesn't mean the physical change, it's just the cross-sampling smooth out the local amplification. So we also observe this issue in the oscillatory variability. If you look at the plot on the right-hand side, for the case outside Seattle, the green dot line, the sigma is actually higher than the Gaudian single station sigma. So the takeaway is resolution matters. The grid spacing must be shorter than the correlation level of non-algorithm based on the simulation. Otherwise, the partial spatial structure just disappear, no matter how perfect your physical are. And the third one, here we want to explain why the epistemic uncertainty in our non-algorithm based on the simulation looks like too small here. Since we have the 30 M9 RUMs on dense grid, the uncertainty is less than 0.1 natural log unit. If we didn't observe this behavior in the observation before, and the key limitation here is that this simulation are based on a single 3D velocity model. So the small uncertainty is simplified just reflect the only one specific model, not a true uncertainty. So to handle this, we have to make assumptions, otherwise the epistemic uncertainty is close to 0 like this. For example, inside the simulation region, we set out the uncertainty of health of the variability. Here is the VS2S. So for the right-hand side map, you can see the side 1 to side 3 is within the simulation. So the bottom is show this distribution epistemic uncertainty is more narrow for the column line here. So in terms of the variance, we are essentially allocating 25% to account for a single 3D velocity model here. And for the outside region, for example, the side 4 here, the bottom, the black curve, you can see have a wider epistemic uncertainty here where because we have a lot of data to constrain it, so we let the uncertainty reach the whole VS2S here, the variability. So to truly quantify the epistemic uncertainty from this non-algorithm based on simulation, we need simulation cross multiple velocity model. But until we have that information, the assumption I just described are needed in the practice when we use in the seismic hazard analysis. And challenge 4 is about frequency contact limitation. The issue is that the 3D simulation are usually work on the longer periods, like the higher than 1 or 2 seconds. So for for a higher frequency, Berman simulation usually use the 1D stochastic methods here. So this means the sine effect or pair effect we see at the longer period are simply missing at the short period. But for engineering, we can just stop at maybe 2 or 3 seconds. We still need a short period ground motion for design. So the simulation frequency range is limit problem, and this is why we need a validation from small earthquake. So define exactly where the reliable period range and okay. So then here just quickly to show the result when we use the non-Gaussian model and based on simulation put into the hazard calculation. So the upper function is really simple. You have your Gaussian model median value, and then you add the non-Gaussian to adjust it. And this non-Gaussian will include like epistemic uncertainty to let it put this information into the hazard calculation. And this one is a reduced standard deviation from non-Gaussian model. So you can see these two sides here, the side 3 and the side 4. And the red line is from a Gaussian model, and dashed line is from non-Gaussian. So for a side 3, it shifts to left because if you look at the right-hand side plot, the side 3 has a really strong negative adjustment term from the non-Gaussian. So it shifts to left and have the steeper slope because we have the smaller standard deviation. And the gray area is the range of fractal. It's like epistemic uncertainty for your non-Gaussian. If we have a narrow range, means you have a more confidence for this side. So for the side 3, because I have more data, more information from simulation, so I have a narrow range. But for the side 4, it's outside the simulation, they will have a wide range for a fractal to let the engineering to know this part maybe need more information. And also resolution issue also can see here, if we use a smaller standard deviation from like a Seattle region, here is the dash line, break dash line, 3 seconds. So it have a steeper slope, but if we use the result from outside Seattle region, it's a bigger standard deviation, and you can see the pink line, pink curve here is close to a Gaussian model. So actually, if resolution is less, we cannot help too much from our model. That's a problem here. So that's my final slide. So we need to multiple rupture scenario, and because we want to separate side and pay fade here. And we also hope the grid side can more smaller, but it should be shorter than the correlation length of non-Gaussian. Then we can have a more better result. And validation is required because we hope can obtain the accurate result and the reliable period range of 3D simulation. The final one is more important because we really need the epistemic uncertainty into the seismic hazard. So if simulation people can simulate like multiple alternative 3D velocity model, provide the information, and we capture the more apparent epistemic uncertainty, then the model will work better. Yeah, thank you.
Thank you very much. Okay. Well, I think maybe what we'll do is we'll move into the breakout. So I think actually, let me share my screen. Our goal is we have 3 breakout rooms. The original idea was we would run these breakouts twice so you could have an opportunity to go into one and then into the other. But I think because we're limited on time, what we'll do is we'll just have you go into one room for, we'll say about 20 minutes. And then we'll have the group note takers, moderators from each room do a short report out at the end. So these are the 3 themes that we've picked for the breakout rooms. Our goal with these is to ask the questions or discuss these questions that are down here for whatever your theme is. So essentially they all revolve around what ground motion estimation in Cascadia needs to address. So have specific ground motion needs for your field not been addressed in the talks? What characteristics are most important for your work or for this theme? what are some of the challenges you see in the current models? And do you see challenges in implementing simulation results? And if so, what are they? So essentially, we're kind of trying to get at what do we need? And then when we think about the science that we're doing in Cascadia, in particular in the simulation space, what are things that we would want to consider? And then that'll sort of tie into the next workshop. So what we'll do is we'll open up these breakout rooms, pick one of these rooms as a theme, and then we'll give you about 20 minutes, and then note takers, if you wouldn't mind having a quick summary in your mind for the report outs. Yeah, so I think maybe what we'll do is do a couple minutes report out from each of the breakout rooms in terms of some of the main points of what you discussed. I don't know if anyone in particular wants to kick us off. Brett?
Sure. I'm going to share my notes just so other people can see what I wrote. So we had a small group, but a really good discussion on ground failure. And I put in bold what seemed to be the key points that came out of the discussion. There was a really good discussion around how high a frequency do we actually need to achieve a stable or reasonable estimate of PGA. And Norm Abrahamson had the great idea of looking at records and high pass or low pass, high cut filtering the records to see where the expectations of liquefaction begin to stabilize. And so I think for the modeling, the simulation community, it would be really great to actually provide a reasonable target. How high of frequencies do we actually need? There's the caveat that computationally it can be done, but in terms of resolving those high frequencies, do you actually have the velocity structure information to get there? And at a regional scale, it would seem like the answer is not really. Duration is really important, and that's not something that had been talked about much in the sessions. And then specific to landslides, topographic effects are really important. Kind of still relatively nascent area of research, more to be done. And we talked finally about the aspect or the directionality of the motion aligning with the slope. And seems like conceptually that should matter, but maybe that there's not enough data to look at it just yet.
Thank you. Before I move to the next breakout group, I guess, are there any thoughts or questions from anybody who wasn't able to be in that room? Okay. Maybe we can go to the next room. There's a room I was in, which is built environment or otherwise hazard and ground motion modeling needs. I don't know if you'd like me to go or if the other group wants to go first.
I could try to go, unless Karen, I don't know if you want to do this.
Maybe you, because it's not finished.
I don't know how to
Our discussion is not finished. Just everything. Yeah.
We talked about a lot of different things. I mean, some of the things that maybe stuck out to me, I think we had an interesting conversation about, it actually was born out of something that Jeff Berman said in his talk about the California experience, and a lot of the assumptions that we make in ground motion models might be kind of biased towards California. And that could be things like maybe even the attenuation relationships that we're using to convert from VS to Q, hypocenter depth, basins, and like what else do we need to re-examine that might have a California bias? Some other things that came up from a hazard perspective, Brad Agard mentioned, it'd be really interesting to know where we've seen ground motions that aren't well predicted by ground motion models. And I think maybe that speaks to we need to be exploiting our small magnitude seismicity in the Pacific Northwest, maybe more than we are currently. And then are those differences due to the source, path, site, basins, etc. Randy Levesque also made the point, we've talked a lot about high frequencies today, but for tsunamis, the low frequency displacements are also really important, and that can be challenging, I think, to validate. I think it's just something that we don't think about as much, like when we're doing simulations, for instance. And then on that theme of validation, we did kind of end, and we cut Albert off at the end, talking about validation and how important that is, and kind of in California, how they've seen that sometimes the simulations don't do as well as the non-ergodic models, but that's challenging to do here when you have so little data, but we need to find a way to work on validation, whether that means going to other subduction zones or, again, that small magnitude seismicity.
Awesome, thank you. And then kind of the same question before we move to the other room, if there's any thoughts, questions, things that came up if you weren't able to be in that room. Okay. I can give a summary of the last room, unless Morgan, you want to do it. Okay.
Nope, go ahead, thanks.
We also had a small group, but there's a few things we talked about. One of them was there's a fair amount of discussion about if there is simulation data east of the Cascades, or if that exists, and that might be useful for. So it sounds like maybe Hanford is one of those, but other facilities. So we talked a little bit about expanding the velocity models and the simulations to the east. In particular, that the longer periods matter more here and less the higher frequency. So it sounds like for that context, at least the ongoing velocity model updates with sort of crustal scale resolution might be useful for that. We talked a little bit about existing scenarios, and in particular, what variability exists in them, and maybe what might be useful. So a lot of that was just kind of summarizing what exists, that a lot of them are mostly full margin, somewhat limited magnitude range, although it sounds like, especially in the COPES project, there's some ongoing work there that's expanding the magnitude range. So it sounds like that maybe ties in a little bit to what Karen was talking about, that there's value in also varying the extent of those in terms of constraining path effects and site effects. And then a last thing, we briefly touched on duration. From the engineering perspective, it sounds like that there's still a lot of open questions on how much that matters, and that different researchers have come to different conclusions, but maybe something to keep on the radar, especially given that ground failure also notes that as being important. I don't know, Morgan, or if anyone else in the group, did I miss anything that you'd like pointed out?
No, I think you've captured it all, but maybe just adding, I think a lot of the work out of the simulation-based, or is it DET working group, will be really important for understanding maybe variations in source effects in Cascadia that haven't really been addressed in the simulations yet, the wave propagation simulations.
Yeah. So that's what we've got today. The next session is going to be on January 29th, and we're going to talk about inputs and data and methodology. So we'll have some talks about what exists for seismicity in catalogs, both in terms of updates for databases as well as potentially validation work. We'll have some talk about that's summarizing dynamic rupture models and how those can maybe be used. Some information on updates on velocity model development, on existing paleo shaking data and how we might be able to use that. And then also some talks on non-ergodic ground motion model development and physics-based methodology improvements. And then we'll have the in-person topical workshop in May. And so if you're interested in attending either of those, we'd really love to have you there. And we'll send updates out to that. And then please send us an email or contact us if anything comes up.